In a previous video, we looked at how to use the Muskingum method to route flow through a channel where the K and X parameters were selected based on recommended guidelines. But what if you already have observed upstream and downstream flow data and want to determine the best K and X values that actually match historical records? In this tutorial, I will show you how to use Excel Solver tool to automatically estimate these parameters and calibrate your Muskingum routing model quickly, systematically, and without any guesswork. Let's get started. In the Muskingum method, channel storage S can be calculated based on the inflow I and outflow Q using this equation. In this, K is the proportionality coefficient and is associated with travel time in the reach. A larger K results in more attenuation, which gives a flatter hydrograph. X, however, is a weighting factor, a weight of inflow versus outflow. This parameter controls the balance between inflow and outflow storage. X generally varies between 0 and 0.5, where X equal to 0 represents a linear reservoir, where storage is a linear function of Q. By incorporating Muskingum storage into the discrete form of the continuity equation and organizing it to find the downstream routed flow Qt, we get the Muskingum formula like this, where coefficients C1, C2, and C3 can be calculated using the equations below. For more information on the derivation of these formulas and the step-by-step calculation in the Muskingum method, please watch our tutorial video on this method. Now let's solve a numerical example using Excel. The observed inflow hydrograph at an upstream point A of a reach, along with the observed outflow hydrograph at a downstream point B of this reach, is given. We want to calibrate the Muskingum routing method for those two hydrographs and find the most suitable K and X values. As can be seen, the time step delta T in this example is 1 hour or 3600 seconds. Let's go to Excel and solve this. To start with, I have listed all required data and formulas for this process. As you can see in this table, we have the observed inflow and outflow values, or let's say upstream and downstream. So both hydrographs are provided here, and also I've created the template of the Muskingum method calculation. There are 3 columns to calculate the 3 terms of this equation, as you can see here: C1 times IT, C2 times IT minus 1, and C3 times QT minus 1, and finally QT, which will be the summation of the 3 terms. And then on top here we have the delta T, which was 1 hour or 3600 seconds. I have also put 2 dummy values for X and K to just start the process. And for choosing these numbers, I have followed the conditions or the constraints that we have. For example, we know that K by right should be larger than delta T. And then X ideally should sit between 0 and 0.5 for the stability, so the numbers are chosen accordingly. And then C1, C2, and C3, the coefficients of the Muskingum formula, have been calculated following these 3 formulas that you see here. To save time, I have done it earlier, so they are like ready here. If I click on it, you can see the same formulas are implemented here. Before I start, there is a condition that I need to make sure it has been fulfilled. And that condition says that for the stability, C1, C2, and C3 should add up to 1. So let me check on that. So if I sum up the 3 values of C1, C2, and C3, that gives me 1, which means that the calculation is correct and the system is going to be stable. Please also note that there are some other conditions. For example, this one, our delta T should sit between 2kx and 2k1 minus x. And because of that, I've already put these 2 because later when I want to define these constraints in the solver tool in Excel, I need to have these values. That's why here, let me do that. So 2kx is going to be 2 times our k value times x. And then for the next one, it's going to be 2 times k value times bracket 1 minus x. And these 2 values are going to be used later in our calculation. Okay, now we start the Muskingum calculation in order to estimate the routed flow in the downstream point B. There are a couple of initial values that I need to start with. For example, our QT generally, if you don't have an observed value, you need to have an assumed value for that. But in this case, since we have observed value, we know that our starting point is going to be 0. And then the first term also, because our first value or even the inflow at time 0 is 0, so practically C1 times 0 gives me 0. The other two terms, because we don't have the previous value of I and Q, which means IT minus 1 and QT minus 1, I just put 0 at the moment, but practically we don't have them, so we assume that they are also 0. Okay, I start with this cell, the first one, so it's going to be C1 multiplying to the I value at the present time, but I need to put $sign behind the coefficient because later I'm going to copy it for the other cells, so I make sure that it will be fixed. And then for the second one, it says that it should be C2 multiplied to IT minus 1, means the previous value. So for me, it will be C2 multiplied to the previous value of I, which is here. And again, like last time, I add the $sign to fix the location. So it is done. And this one, I'm going to have C3 multiplied to the previous value of Q, which is here. And the only thing I need to do, like last time, is adding the $sign. And that's it. So the last cell is going to be simply the summation of these three terms that we have calculated here, following this formulation. So what I need to do is just simply select, and then after that I copy this down all the way for all the time steps up to here, and that's what I get. So these are the estimated values that I've got using the Muskingum equation, but we know that our X and K values are some dummy numbers that I just chose, and they are not definitely correct, because when I compare the estimated values versus the observed values of the outflow or flow at point B, the downstream point, we can see that the numbers are not matching, they're different. So in order to have a kind of numerical understanding of this error, I'm going to calculate squared error here. So that is very simple. What I'm going to have is the observed value minus the estimated value with a power of 2. And then what I'm going to do is just simply copy that for the other cells. You can see that these are the values that I get. And then I need to also find the sum of squared errors. So here the calculation is very simple. I just sum up the values from this cell all the way down to the last cell, which is this one. So that will give me the summation of errors. Okay, now it's time to use the solver in Excel in order to find the best set of K and X that can minimize our SSE, or the sum of squared errors. So to do that, first you need to activate the solver tool in your Excel. So for that, you click on the file, go to the options, and then add-ins. Here you need to search for the solver add-in. It's here. I click on it. After click on it, click on go, and then OK. You accept it. It's going to be added. And where you can find it, it's in the data tab, and it's here in this corner. So now you have it activated here and you can use it. So to start the calculation part, you click on the cell that you want to optimize. But before that, before I lose this number, because it's going to change very soon, I'm going to write it down for myself for the record that my dummy values of X basically gave me this value. So SSE, I call it initial value. So that's what I've got, and you will see soon that by optimizing X and K, this error is going to be much smaller. So I click on SSE. After that, I click on solver. This window pops up, and that's where I need to define some parameters in order to ask Excel to find the best K and X for me. So the first thing you need to set here is the objective function. And for us, it's going to be this cell. That's what I'm going to play with. And we are interested in minimizing the values of this cell. After that, the question is, okay, by changing what variables? Our variable is X, I put a comma, and K. So these are the two numbers that are going to change. The next stage is the constraints. If we have any constraints that need to be fulfilled, definitely we have. The first one is that I need my K value to be larger than my delta T, which is 3600 here. I click OK. So this condition is added now. My next condition is going to be about X. So I'm expecting my X value to be, first of all, larger than 0. And then the second part of the condition is that my X value should be smaller than 0.5. And if you remember, I also created the 2kx and 2k1 minus x here, and this was because of this condition that I have. And now it's the time to play with it. So first, I'm expecting my 2kx to be smaller than delta t, 3600. And then the second part of the condition says that basically my 2k times 1 minus x should be larger than the 3600, and I click OK. So these are the 5 constraints that I'm going to have based on the conditions that we originally had. So now we are ready to click on solve. But before I do that, I bring this window so you see what is going to happen at cell X and K. Please look at here. So when I click on solve, it does the calculation, and that fast you get the final answer. I click on OK to save it. So you see that my 0.25 dummy value is now 0.2, and my 4500 dummy value for K is now 4082. And you see that the sum of a square error is now much smaller than the previous value. 38 is now reduced to 3. So that gives us the idea that how well the optimization has been done. And even by looking at the values here, we can see that the numbers now are much closer to each other compared to those values that I had based on the dummy X and K values. I have also plotted the inflow outflow values. The inflow is the blue hydrograph, and then the outflow is basically the two hydrographs that I have plotted here. The gray color is the observed values, and then the black dashed line one is the estimated one after calibration. And you can see that it is perfectly overlaying the observed values. So that shows that the calibration has been done quite well. Of course, if you zoom in, you see that there are still some minor errors there, as we can also see it here in the numbers of SE, but they are really minimal. And when we look at the hydrograph, it is perfect for the sake of calibration if you want to look at it. So that's the procedure. So you can see that you really don't need to guess the numbers. You don't need to do any kind of manual calculation or manual play with the K and X values in order to optimize it. This tool in Excel can easily help you in few seconds to solve it and find the best answers for that. If this video helped you, please check out the What I Do How playlist for more practical content. Thanks for watching. See you in the next one.